We're going to talk about the nucleus. We talked already about the fact that atoms are about 10 to the minus 10 meters in size. The nucleus is about 10 to the minus 15 meters in size. What happens inside of that tiny, tiny space is very important and breaks some of the rules, including the conservation of energy that we've talked about already. Last semester, we talked about the three fundamental forces of nature. Gravity, we spent a fair amount of time on, and you all have solved lots of problems using gravity. The other two fundamental forces of nature are called the strong nuclear force, sometimes just called the strong force, and what's known as the electroweak force. We are going to focus in this chapter on these two forces. And the electromagnetic force we know about. That's the force that binds atoms together. The electrons that are negatively charged are attracted to the positively charged nucleus because it has protons in it, and that is the Coulombic attraction between charges that are opposite. Gravitational force is what holds the planets in orbit around the sun, and the Earth and the sun in orbit around the center of the galaxy, etc. The strong force is what binds the nucleus together. Not the atom, but the nucleus. You might say, well, hey, there are protons inside this nucleus. Don't they repel each other? Because like charges repel. The answer is yes, they do. The Coulomb force, this force here, this electromagnetic force, says those protons need to repel each other. But the strong force overcomes the Coulomb force on very small length scales of order 10 to the minus 15 meter. We'll talk about that. We'll talk also about the weak force that governs one form of radioactive decay, and then talk about the fact that the weak force and the electromagnetic force, the electric force and the magnetic force, all three of those forces, electric force, magnetic force, and weak force, are different manifestations of the same fundamental force, which is called the electroweak force. So first, a little bit about nuclear structure. So this is a nucleus, and the size of the nucleus, as we know, is about 10 to the minus 15 meters, depending on the nucleus that you're talking about. It consists of neutrons, here shown in red, as well as protons, here shown in blue. And the masses of the protons and the neutrons are very similar to each other. So proton mass in kilograms is 1.67 times 10 to the minus 27 kilograms. You don't have to memorize that. I'm not asking you to memorize all these numbers. If you need them in homework, you can look them up in the book or online. If you need them on the test, I will supply them on the test. Whereas the neutron, also 1.67 times 10 to the minus 27 kilograms, but this fourth digit, or the third digit after the decimal place, is slightly different. So they're very, very close in mass. The electron, on the other hand, is as you have seen in other problems, 9.11 times 10 to the minus 31 kilograms. It's about 1/2000th of the mass of a proton. It's very, very light compared to the proton and the neutron. The charges we already know about, electron charge and the proton charge. The neutron charge is 0. The overall hydrogen atom, which has one proton, one neutron, one proton and one electron in it, that overall charge is also 0 because the positive and the negative cancel each other out. We'll also use something called the atomic mass unit. It's defined as 1.6605 times 10 to the minus 27 kilograms. So as you can see, the atomic mass unit is very similar to the mass of the proton and similar to the mass of the neutron. In fact, the mass of the proton is just a little bit greater in mass than this atomic mass unit. It's 1.007 atomic mass units, and the neutron is 1.008 atomic mass units. You don't have to memorize that number. It'll be supplied as needed. Okay, we want to define some words here that we'll be using in this, and there are 10 concepts in this chapter, but they're all quite simple. The nucleon, a nucleon is a neutron or a proton. So the neutrons and the protons in a nucleus are collectively known as nucleons. They're not, they're particles that reside in the nucleus is the way to think about that word. And the number of nucleons is given by this equation here. So A is the number of nucleons. It's called the atomic mass number. That's where the A comes from. And the mass really depends on the number of protons and neutrons, because the number of electrons hardly matters to the overall mass of the atom. So that's one way for me to think about it, at least. It's the number of nucleons, sometimes called the nucleon number. Lots of words to describe the same thing. The atomic mass number is equal to the nucleon number is equal to the number of nucleons. So you add up the number of protons and the number of neutrons to get the total. And in fact, that's just this equation here. The atomic number is the number of protons, sometimes called the proton number. That's Z. And this determines what kind of a nucleus it is. It determines what element we're talking about. You can change the number of neutrons in an atom and still have the same element. Those are called isotopes of the element. So then the neutron number is the number of neutrons. And so if you add the number of protons to the number of neutrons in a nucleus, then you'll get the number of nucleons. It's as simple as that. Nothing too fancy at all about it. The symbol for the nucleus, if you have an element whose chemical symbol is X, if it were iron, that would be Fe for iron. The symbol for the nucleus is the atomic number of nucleons, as a superscript in front of the chemical symbol. And then the proton number, or the atomic number. This is why it's so confusing, because this is called the atomic number, which is the number of protons. This is called the atomic mass number, which is the total number of nucleons. But we'll try and make sure it's clear in every problem and on tests, etc. So, so we're talking about the total number of nucleons here and the number of protons here that is listed. This number A will always be greater than, than Z. So for example, the hydrogen atom has one proton. That means that Z is 1. It has no neutrons, and A is Z plus N, so A must be 1. There's one nucleon. And so the A goes up here, the bigger number, that's 1. And Z goes here, the smaller number. In this case, the two numbers are the same because there are no neutrons. And then H is the chemical symbol for hydrogen. Helium has 2 protons, Z equals 2, 2 neutrons, N equals 2, and then 4 nucleons. 2 plus 2 is 4. So that's the symbol for the helium-4 nucleus. You can also, there's another isotope of helium, has the same number of protons, still 2, but another isotope of helium is helium-3. So as we've said, the atomic number defines the chemical element. If it has 2 protons, it's helium. If it has 1 proton, it's hydrogen. If it has 6 protons, it's carbon. And then changing the neutron number gives different isotopes.